because okay, today we're on day 2, algebra. So the first thing I want to talk about today is combining like terms. So if you've not done a lot of this before, this may seem bizarre, but math is like a language with its own vocabulary. If we're talking about terms, what is a term? Numbers are variables that are separated by plus and minus signs. Plus and minus signs. So in these examples here, 8 plus 2x plus 3y to the third power, there are 3 terms here. It looks like more than that, but you got to remember 8 is a term by itself, 2x is a term by itself because it's bound together with the x by multiplication. 3y to the third is an exponent in multiplication, so the 3 and the y to the third power all go together, so there are 3 terms there. There are 3 terms in the next equation also. Y is a term, negative 2x is a term, and 8 is a term. So like terms are ones that we can combine. They have the same variable and the same exponent level. Otherwise, they're not like terms. And this is where people really start to struggle sometimes in algebra, because now we're talking about variables that maybe don't make a lot of sense. But if you look at this table here, the terms that are alike are the ones that look alike. 3 and 5 are like terms. Those are just integers. Those can be combined. 3 and 5x are not like terms. Those don't go together because 3 is an integer. 5x is 5 times x. That's a separate problem unto itself. Next row, negative 5x and 9x, those are like terms. And now we can combine the coefficients. The coefficient is the number in front of the variable. And that's true no matter what kind of term you're talking about. So negative 5 and a positive 9 would leave us with 4x. It's like saying we got 5 negative x's and 9 positive x's. Well, 5 of those are going to cancel out and you're left with 4 positive. But the next example here, negative 5x and negative 5y, those are not like terms. That is the sort of the classic apples and oranges example. If you go into a store and you buy apples and oranges, you still have apples and oranges when you come out. You don't combine those unless you're talking about fruit. So they don't go together. So you have to look at the coefficients, the numbers that are in the front, and the variable part to see if they're going to go together or not. And every term is going to be like that throughout algebra. No matter how complicated it looks, you still have to identify the terms that go together. This fourth row, negative 11xy and 2xy, those are like terms. So the coefficients together would give you negative 9xy. In the second box here on that fourth row, those are not like terms because one of those x's is to the second power. You have to look at the exponent level as well as the lettering itself. So when you start combining these, this is really where the true algebra begins, because in this example here, where it says simplify, this is an expression. We're going to combine like terms here. The like terms, anybody can tell me one or two of those?
5 and 7.
Yep, 5 and the 7 go together, so there's 12.
And then
7a and minus
and
4a, good, good. So 7 minus 4 is 3. We're left with 3a, right? Great example of combining like terms in a fairly simple expression. Next one, very similar. 6 plus 9x plus 1 minus x. Seven plus 8x. Because I got 9 positive x here and 1 negative x. And the thing about these like terms, if you see just a single letter, like this example up here on row number 2, says y squared. The coefficient is actually 1. If all you see is a single letter, you know the number is understood to be 1, or like negative a to the second over here, it's understood to be negative 1. So when you're combining these like terms, you have to remember that, because this example, 6 plus 9x plus 1 minus x, that's a negative 1x that we have to combine. Now this last one looks fairly complicated. So you kind of have to go through the list and identify the ones that go together and just check them off, starting typically with the largest or the highest exponent value that's there. So I see 2 terms here which have x squared with them. Right. 12x squared minus 2x squared is 10x squared. Oops, I gotta do that. Different. Okay, now we got we have x's, yeah. We got 6 positive x and negative 18x minus 12x. And then we got y terms, negative 7 and plus 12 would give us 5y. Right, and all those would be strung together. There we go. And that's your answer. We don't know what x or y stands for, so we can't simplify it any further. And that's pretty much the way combining like terms is going to work, no matter how complex the problem is. You're always looking at the coefficients to combine with the other coefficients of similar terms. Questions, anybody? I hear somebody has got their television on in the background. Can you mute yourself, please? All right, now we're going to start looking at some multi-step equations. The only difference between these and the ones that we looked at with the 2-step equations that we start off with today is you got more steps involved. So the first thing that's shown here is just what we're just doing, simplifying some expressions by combining like terms. Integers go with integers. The same letters go with the same letters. The other thing that you're going to have to deal with a lot of times with equations or expressions is the distributive property. And you have to remember these multiplication rules. Negative times a negative is a positive. positive times a positive is also a positive. So if the signs are the same, you're going to get a positive number or a positive variable. The other two signs are different, so those always end up negative. And here are 4 examples of distributive property problems that you have to simplify. You got to take that number that's on the outside of the parentheses, multiply it against each number on the inside of the parentheses. So this first example would be 6 times 5p, which would be 30p, and 6 times 4, that's 24. So the simplified version is 30p plus 24. And that's as far as you can take it, because that term with the variable is not like the integer. You cannot combine those. This third example can be a little bit tricky though, because now you've got to remember this is a -4 that you're multiplying by, and a negative times a negative gives you a positive, and you have that in each case. You got 24 with -4 times -6 is a positive 24. -4 times -6 is a positive 4x. Excuse me, -4 times -x, positive 4x. So you could write that as 4x plus 24. The biggest thing that we're dealing with in all these equation solving is using inverse operations. Some people say opposite operation. Means the same thing. Addition and subtraction are opposites. Multiplication and division are opposites. And we're going to use that. And that's why if I ask you what kind of a problem is it, that's the first thing you need to identify. Is it, there's only 4 operations: add, subtract, multiply, and divide. So it's got to be one of those 4. If you identify it as addition, then the opposite's going to be subtraction. If you identify it as multiplication, the opposite's going to be division. And that's what equation solving and simplifying expressions is all about. Using those opposites to eliminate terms from one side of the equation so that you can get a variable by itself, or to at least to eliminate multiple terms or parentheses. So, first question. We have an equation that's got 2 x terms on the left. Okay, so my like terms are the x terms. 8 minus 5 is 3. On that side, I still have a plus 1, and it equals 10. So I've simplified it a little bit. Now, what's the next thing I should do?
Do you subtract the 1?
Yeah, I don't know who said that, but that's absolutely what I would do. Most of the time, you want to leave your variable term to the last, because I need to get rid of that 1 first. We got to get rid of everything that's on the same side as our variable. And then the variable is left to be dealt with at the very last step. So we end up with 3x now, which equals 9. And if you notice, we had a plus 1 here, so our opposite is a minus 1. If you see that as addition, then you need to subtract. And I use these terms pretty much interchangeably. Plus is the same as addition or positive. Minus is the same as subtraction or negative. And now I'm almost done, but I don't quite have the x by itself. Divide by 3. Yep. Divide by 3, both sides. X equals 3. Now here's a problem with distributive property component. And our variables on the right-hand side, that doesn't really make any difference with an equation. But I got to do this distributive property multiplication first to get rid of that parentheses. 24 equals 8 times 8m, 64m. Wow, that's going to be a big number. Plus 40, 8 times 5, 8 times 8m, plus 8 times 5. Now what? Oh man, I just saw a mistake here. I forgot my minus sign. That's a
So do you
killer.
add 24 on each? Is that what you do?
Okay, you could do that if you want. But what do you have left then on the left-hand side?
Subtract 40.
Subtract 40. I'm going to subtract 40, right? If you add 24, you're shoving all the terms onto the right-hand side. We're trying to eliminate the terms. We don't want more terms over there. We don't want to sort of make matters worse. So the formatting is off here, but I'm going to subtract 40 from both sides. There we go. I can shove that over. Start off looking like it was going to be a pretty big number. See, because now I get rid of this 40 over here. I'm still dealing with numbers on the left side. That's okay. Negative 40 and negative 24. Negative 64, right. This is the other part of the integer rules that you have to remember. Same sign together, we add them. 64m, and I remember my minus sign. That's the biggest single mistake area in algebra, is forgetting the sign. So now I can divide both sides by 64. Yep, good. Whoops. All right, now, would you guys go ahead and try this one? I'm going to pause things for a minute. This one's got a little bit of a trick to it.
Any man that doesn't want to cooperate, I'll make him wish he hadn't been born.
Anybody got any answers? They want to volunteer? All right, good job, Max.
He doesn't want to cooperate, I'll make him wish he hadn't been born.
I hear John Wayne there. Somebody's watching a John Wayne movie. Please mute.
Forgot I wasn't muted anymore.
Yeah. Yeah, that happens a lot on these Zoom meetings. So, so if you got a positive 4 here, you did this one correctly. The trick on this one is add this minus sign in front of the parentheses. What that does, it's still a distributive property problem. If you can imagine that that's a -1, or it's just a minus sign that you need to distribute against each of the terms that are on the inside. So it doesn't change anything on the left-hand side. We still have -25. Get this over here. Equals, now we got -1. Oh, it's supposed to be equal. -6x. I'm trying to do this in the dark here. It's a little challenging. So I distributed that minus sign against each of the terms in the parentheses. It's just like multiplying by -1. So now I'm confident I got the signs right. So now I need to add 1 to both sides. Which leaves me now with -24 equals -6x. Not quite. Now we got a negative divided by a negative. We divide, what? That's right. We divide that -24 by -6 and we get +4. And if you're not sure about that, plug it back into the equation. Any place in here, -1 minus 6 times 4, well, that becomes -24. And then put another -1 with it, -25 equals -25. You can always do that. And this is a situation that you'll see a lot in algebra, that just with a minus sign in front. Questions, anybody? Okay, I got another one of those to look at here real quick. I get it open. Okay, so far we've just had variables on one side or the other of the equations. You're going to see equations where the variables on both sides. This is what we've been doing so far. This example here under describing equations is just a two-step equation. The variables on the right, there's one coefficient here, which is 9. The constants are 47 and 2, because we know what those are. Those don't change. Remember, a variable is anything that's an unknown or anything that is changeable. So this starts to look like a more complex problem with multiple variables. At least they're the same variable on the right-hand side. We've got a distributive property component here that you have to deal with to get rid of that parentheses, then probably combining like terms. And then you're going to go through the same process of either adding and subtracting, multiplying or dividing to get terms, to get your variable by itself. Here's the first example where you've got a variable on both sides of an equation. First thing that you want to try to do, anybody have an idea? We got somebody saying, Ariana's saying we should get the V's together on the same side, on the left side. That's a great idea. Probably the right idea. First thing we got to do is combine the terms on the left. We got 1 plus 10V on the left equals, and we got other like terms on the right, 8V minus 3, okay? You always have a choice about where to put those variables. You can put them on the right or on the left. In an equation, it does not matter. Later on, when you get into inequalities, it will matter. So now you've got multiple steps to go through to get this 8V eliminated. Plus 8V? How does that cancel?
Oh, okay.
And we can cancel entire terms like this. As long as we have the coefficient the same and the signs are opposite, they will cancel. That's our goal. We want to get rid of the, if we're going to move them to the left, then we got to get rid of it on the right. So 8V and a negative 8V, this is like 8 positive V's, and then you have 8 negative V's, those are going to cancel out. So the only difference with these and other simpler equations is just more steps. So you end up with 1 plus 2V equals -3. Now we gotta, since we made the decision to put the variables on the left, we gotta get rid of that 1 from the right. I mean, from the left to the right, I'm sorry. Yep. So now we're at 2V equals -4. And then divide by 2, right? And you get V equals -2. So the only difference here is you're doing more steps. It's the same process over and over and over again. Add for subtract, multiply for divide. Usually the division is the last step in the process. Trying to see if I got another one like one Ariana was showing me earlier. Well, this last problem, this focus question 5, looks very complicated. So what do you want to do first? Yeah, let's get rid of some of those parentheses. Can't type in here for some reason. There we go. So what do I have on the left now? Good. Remember the sign. All right. Means the same to me. It's okay. Okay. Right. The 7K is by itself for the time being until we get rid of the parentheses. Your numbers are backwards. I'll take 56, -56K. Yeah. That's a lot of K's in there. Okay. Sounds good. Okay. Before we do that, though, I would like to combine them on the right because I'm not sure how many I'm actually moving or which side I should move them to. 7 and -56 leaves me with -49. I have negative 56 Ks and 7 positive Ks. All I'm doing is combining them. I'm not multiplying. The only time you're going to change the sign from negative to positive is if you're multiplying. Same sign. Right. So now I look at this and I got a higher number of Ks on the right. So this is definitely one that I would want to move to the left. I'm going to add 49K to both sides. Yep. The K's all cancel on the right-hand side. Now I have K minus 16 equals 7. I didn't mean for that to be capitalized. Now I got to deal with that minus 16. That's the only other term that needs to get moved. Yep. Well, you guys are going to be good at this. This is sounding pretty easy for y'all. I don't have a way to divide the sides here, but yeah, I'm adding 16 to both sides.
Oh, okay.
So K should equal 23. Why does it keep? What's 7 plus 16?
Oh.
See, this 7 here is still remaining on this. Oh, you know what? And it's a negative 7. I forgot the sign. Good. I didn't do that on purpose, but believe me, it happens. If you guys are with me, you'll see that. Yeah. And Jessica, was that you that called me on it? Oh, good. Somebody did. That's all I care about.
Sorry, it threw me off because I was sitting here, I was like, that doesn't look right.
Well, if it doesn't look right, it's probably not right. And that's a good lesson to remember for when you're doing your own work. And I didn't do that on purpose, but I do make mistakes.
We all do, it's part of life, right?
That's what I'm told. So I'm trying to get back to Odysseyware here for algebra. Anybody got questions so far?
Answer questions on that one question I asked earlier.
Okay, well, we can look at that when we get through the Zoom session. So the next thing after the first quiz is this section on variables on both sides. That's just what we were doing with those last examples. The thing about Odysseyware that some people like, some people don't, but it does show you the step-by-step solutions for all of these examples. So if you need that step-by-step, it's here, it's there for you. And then the examples are going to follow on that are going to be very similar. So if they're asking you, this like this question number 4, what's the most efficient method? In the first step, if the first step in the solution of this equation is to add 10, what should the next step be? Okay, well, think about that. If they're adding 10, that means they're eliminating the 10 from the right-hand side. Okay, if you're going to add 10, you're going to get rid of that negative 10 on the right, and the 10 is going to go to the left. So then you're going to have plus 10 minus 8 minus 7x equals negative 5x. If you add 5x, now you have nothing on the right-hand side. You want to add 7x, right? Because once you make whatever decision you make, if you're pushing terms from one side to the other, then you have to do the opposite with the other terms. If you go from right to left with the integers, for instance, then you got to go from left to right with the variables. For me, I like to deal with the variables. I like to make that decision about the variables first, because then that determines how I solve the rest of the problem. If I make the decision I'm going to keep my variables on the left, then I know my integers all have to go to the right. And you can make that decision any way that you want with an equation. Because up here, it says the law of symmetry, the symmetric property. It seems obvious when you look at it. A equals B. Well, if you turn it around, it's still going to equal, A is still going to equal B, even if it's written B equals A. So it doesn't matter which side of the equation that you put your variables, it's still going to be, it is an equation. It's this equals that. So you can write it any way you want. You can have the variables on the left or the variables on the right. One thing that I try to avoid, though, is I don't like negative variables. So if I can make the variables positive with that first decision, I'm going to be happier, because you've already seen how many times I forgot the minus sign here doing those examples. And I know that's the biggest mistake area. So I want to try to eliminate that possibility of a mistake right at the beginning. Make my variables positive. So the next section there is about combining like terms. We've just done a bunch of that also. The thing about combining like terms and doing these equations is we've got to keep our equations in balance. That's where that golden rule comes up. Whatever we do to one side of the equation, we've got to do to the other side of the equation. Now, this is the first time that I think Odysseyware starts to talk about solution sets. So we need to look at this real quick. Equations typically are going to have one solution. X plus 3 equals 9. You know the only possible answer for that is x equals 6. So there's one answer most of the time for equations.
This equation is an example of a linear equation in one variable. To be a linear equation, the highest exponent on any variable in the equation must be 1. So these other equations are not linear equations. When we solve linear equations by combining like terms and using the addition and multiplication properties of equality, there is just one solution or value that makes the equation true. In this example, the solution set is -2. There are a couple of exceptions to this rule, though. Take a look at this equation. When we combine like terms on each side of the equation, we end up with 2n plus 4 equals -5 plus 2n. Then, when we use the addition property of equality to isolate the variable term on one side, the variable terms cancel each other out, leaving a contradiction.
So think about this for a minute. You know, I said usually there's one solution for an equation. Well, here's an equation where all of our variables were eliminated. They canceled each other out. Didn't matter which side we would have moved that 2n to, they would have canceled each other out. And so you end up with what she calls a contradiction. This is not true. And when you end up with an answer like this, 4 equals -5, you know that 4 does not equal -5. So if it's not true, you have no solution. There's no possible number you can replace n with that's going to give you a correct answer. So this is one of those exceptions with equation rules. When you lose all your variables, they get all canceled out here like they did here on both sides, and you end up with an untrue statement, something that's false. It's a no solution problem. So what you're going to find then is that you really got 3 options with equations. You can have one solution, you can have no solution, or you can have infinite solutions.
4 does not equal -5. This equation actually has no solution. There is no value that can be substituted in for the variable that will make the original equation true. The solution set for this equation is the empty set. Here's another example. In this equation, after simplifying each side of the equation, we get 3y plus -4 equals -4 plus 3y. Then when we isolate the variable term by adding -3y to each side of the equation, the variable terms again cancel each other out. This time, however, we're left with a true statement. -4 equals -4.
Big difference here. We've lost all our variables again, but we end up with -4 on the left side, -4 on the right. Yeah, Jessica? Yeah, yeah, yep. You just, and that's what I would expect. You would write no solution. Yep. This is one though that has infinite solutions, because now it doesn't matter what you put in here for y, you're going to get a true statement in the end. Infinite solutions, right?
We did not find what one value of y makes the original equation true, though. That's because every value for y makes this equation true. Try substituting any real number in for y, and you'll get a true statement. The solution set for this equation is all real numbers, and this equation is called an identity. So there are 3 possible solution sets for a linear equation. If, when solving, you're left with the variable equaling one value, then there is one solution. Most of the linear equations that you'll solve will have one solution. If, however, the variable terms cancel each other out, then there is either no solution or there's an infinite number of solutions. If you end up with a false statement, such as 9 equals 10, then there is no solution. If you end up with a true statement, such as 9 equals 9, then there's an infinite number of solutions, and the solution set is all real numbers.
I want to focus on that for just a second here, because this is an important concept when we're talking about solutions. When we get into inequalities, solutions are defined differently even than these 3. But for equations, these are the 3 options that you'll run into as long as we're talking about linear equations. In other words, straight line equations. Anybody have any questions about that? That's the main thing I wanted to focus on with that part of that lesson. Distributive property, I think we did quite a few of those already. The last piece I wanted to look at here is something called literal equations. People really get confused by these because now we're talking about equations that mostly are variables. This example here, this formula, D equals RT. That's the formula for distance. It equals rate times time. We can solve this equation for any of those variables. We can manipulate it so that we can move these around. And for these literal equations, these are typically formulas. If we know 2 out of the 3 variables, we can solve it. But most of the time, you're just going to be manipulating the order. And we do it by the same operations as before, adding, subtracting, multiplying, and dividing, whichever the opposites are.
Literal expressions are often used to state formulas. Formulas are general relationships that are relevant in a great many circumstances. Just like the equations you have been working with, these literal equations can be manipulated to solve for different variables. Dan wants to fence in his yard. He has 240 feet of fencing and wants to fence in a rectangular space in which the length is 3 times its width. How wide and long should each side be? Start with the perimeter of a rectangle. Perimeter is 2 times the length plus 2 times the width. This is an example of a literal equation. Next, substitute the fact that the length is 3 times the width. That means length equals 3 widths. Substitute 3W for L. Substituting in what is known, 240 equals 6W plus 2W. Dividing both sides by 8 makes W equal to 30. That means the width of Dan's yard will be 30 feet. Since the length is 3 times the width, Dan can find the length of his fence to be 90 feet. To make sure the answer is correct, add 2 lengths of 90 feet each, plus 2 widths of 30 feet each, for a total of 240 feet. Here's another example. There are some boys in a class. The number of boys is 3 more than 4 times the number of girls. If there are 28 students in class, how many boys and girls are there? Let G equal the number of girls in the class. That means 4 times the number of girls plus 3 equals the number of boys.
The thing to watch out for here, and you hear how he's taken these word problems. I know a lot of people don't like word problems, but he's taken these word problems and he's translating them into equations. And these are very literal because he's got an actual example here that he's trying to solve. So if you just look at this equation, G is the number of girls. There are 4 times as many girls plus 3 that will give you the number of boys in the classroom.
Plus 3 equals the number of boys. Finally, the number of girls plus the number of boys equals 28. Add like terms. 5 times G plus 3 equals 28.
So most of what you're going to see in this literal equations section are equations like this. This first multiple choice question. Does anybody recognize what that equation is for? This is a scientific equation. I'm not asking the question here what C and F represent. You said variables, and that is correct. But what is this equation for? What do you use this for? Does anybody know? That's okay. It is the equation that's used to translate temperature from Celsius to Fahrenheit. F stands for Fahrenheit. That's the way temperature is measured in America. If you go to Europe and to most parts of the rest of the world, their temperature is measured in degrees Celsius. 24 degrees Celsius doesn't sound very warm, but that's about 75 degrees Fahrenheit if you were in America. So if you travel other parts of the world, of course, now your phone app is going to give you the correct temperature in whatever location that you're at, if you want it that way. But this is a good example of a literal equation that is used in more of a scientific setting. If you know that it's 20 degrees Celsius, you can figure out how much that translates to in Fahrenheit. So that first example I talked about, distance equals rate times time. If you're going to solve for a different variable, they're showing that you're using the reciprocal here to multiply against. Well, it's the same thing as dividing. If we wanted to solve this equation for t instead of for the d, then we just need to divide by r. Because those letters RT together, and I'll show you what it's a little hard to read on that Odysseyware. But here's the formula. Distance equals rate times time. Well, if I know the distance and I know the rate, I need to find how much time is going to be involved. So if I divide both sides by r, the r's cancel. It's just like 4 divided by 4. 4 divided by 4 is 1. Anything divided by itself equals 1. So now I can figure out how much time it's going to take me on a trip. And I do this all the time. I do a lot of driving, long distance driving. If I have to go 500 miles and I can only average 50 miles an hour, how much time am I going to spend on the road? Come on, guys, cancel some zeros here. 50 divided by 5 is 10. Anytime you've got numbers end in 0, those will cancel out. Strike them out of there. So that, if I can only average 50 miles an hour on that 500-mile trip, it's going to take me 10 hours.
Why wouldn't you cancel the other 0? Because there's no 0 at the bottom?
No, because these zeros here that I canceled are both in the ones place. This next 0 is in the tens place, and the other number, I have a 5 in the tens place. So they got to be the same to be cancelable. So that's going to take me too long. I want to figure out if I can average 70 miles an hour. It probably means I'm not stopping. But now it's going to be 7 point something. What's 500 divided by 70? .14 hours. 7.14, that's how much time. So if I can drive a little faster, I can cut almost 3 hours off my travel time. And if you use Google Maps or you use Waze or anything like that, that's what they're doing when they're telling you how much time it's expected to take you to get from one place to another. If you look for directions and you want to know how much time is involved, that's the formula that Google is using to calculate it. So that pretty much gets us through the first 2 quizzes. So again, tomorrow I should be available if you want to text me, if you got questions, if you get stuck on something, especially if you've ended up with getting blocked after 5 attempts, that's when you need to text me, because those quizzes are going to be locked after 5 tries. I might be able to reset 1 or 2 questions that maybe you messed up on. I did that for somebody yesterday, and they dramatically improved their grade for that quiz. So don't feel bad if you don't get it right the first time around. This is all about practice, and it's going to take some time to figure out what these processes are and implement them correctly in the situations that the quizzes are requiring of you. So any questions, anybody? All right, I'm going to stop our recording.